hopefully you can hear me okay. I think you can. Thank you for that very kind introduction. Let me share my screen here. Do full screen. Great. Hopefully you can see my slides now. So yeah, it's really a pleasure to be able to come and speak to your group today. Unfortunately, not in person. I did get to visit the Karolinska Institute maybe about 18 months ago. So hopefully there'll be a chance for another visit someday. And it's especially nice to be able to talk your first seminar in this series. And I'm certainly going to be signing up to your mailing list for the future seminars as well. So what I want to talk about today is some work on using negative control outcomes for estimating causal treatment effects in an entirely treated cohort. And I'll tell you the context of that in a minute. Let me start by just acknowledging my collaborators on that, particularly Simon Newsome, who was a PhD student at the London School and has now moved on to Novartis. So this work was a component of Simon's PhD thesis. It's moved on a little bit also since then, but much credit for the ideas, many of the original ideas go to Simon. Rhian Daniel was Simon's co-supervisor with me, and acknowledgements also to our clinical collaborators, Di Bilton and Siobhan Carr. So as Anthony said, I work a lot in the area of cystic fibrosis. And as you probably know, so cystic fibrosis, or CF, it's an inherited, it's a chronic progressive condition. And it's one of the most common inherited diseases. It affects, in the UK, more than 10,000 people. And some decades ago, it was a disease from which people often died, unfortunately, in childhood, but things have really improved dramatically for people with CF in recent decades and years. Life expectancy is now in the mid to late 40s. And that's really come with improvements in treatment and care. And something especially exciting that's been happening over the past few years has been the development of these new precision medicines, which don't just treat the symptoms that people with CF have, but they target the underlying defect. And these medicines are called CFTR modulators. And CF, so it's a genetic disease, but there are actually a large number of mutations involved. And these particular treatments work for people who have specific CF causing mutations. And today I'm going to focus on one of these treatments, which is called ivacaftor, or its brand name is Kalydeco. This was really the first of these CFTR modulator treatments to be developed and introduced. In the UK, it was licensed in 2012, and very quickly after that, almost everyone who is eligible to for that treatment on the basis of their genotype started to use it, gained access to it through the National Health Service. So this treatment works for people who have what is called a gating mutation, which is a particular subset of CF causing mutations, and these are present in about 5% of the UK CF population. So, as you can imagine, there have been quite a number of randomized controlled trials looking at this treatment, ivacaftor. These tend to have looked at outcomes, well, over a different range of follow-up times, but from 4 to 48 weeks. Primary outcome has been the absolute change in people's lung function, which is sort of the major problem that people with CF have is poor lung function. And that's measured using FEV1% predicted, and a number of secondary outcomes have also been looked at. But as you can see, these randomized trials have short-term follow-up, whereas the patients are likely going to be using this treatment for many years, the rest of their lives, potentially. And so there's been a lot of interest in using observational data to study the longer-term impacts of these treatments, and also in the complete eligible population, because some of these trials have also been restricted to subsets of the eligible population, in particular people whose lung function is in a certain range. So we have access to this very nice data from the UK Cystic Fibrosis Registry. This is a secure centralised database of people with CF in the UK. It's hosted by the Cystic Fibrosis Trust. And data are collected at annual review visits through the National Health Service care that people with CF receive. And a very nice thing about this database is that it has in it, I think now over 99% of the CF population in the UK. And at every annual review visit, lots and lots of measurements are taken, including information on what treatments people are using. So how can we use this data to try and investigate what the longer term effects of this treatment, ivacaftor, are? Now, the issue here is not really a problem, it's a very good thing. Everyone who is eligible for this treatment is now receiving it, but that creates a challenge for us in that we need to think of what a suitable control group is that's going to help us in estimating the effect of this treatment. So there's been quite a number of studies now over the past few years which have used registry data both in the UK, France and the US to look at this question. Some of the references are given there. So these prior studies have done one of two things. And I'm going to think about the setup. I'm going to use these pictures where I think about the different groups of people that we have. So I'm imagining, I'm calling eligible people, that's people who have a genotype which makes them eligible to receive this treatment, ivacaftor. And then I'm dividing sort of time into the pre-ivacaftor era before 2012 and the post-ivacaftor era after 2012. So some of those studies have done a sort of before and after comparison to estimate the effect of ivacaftor, looking at people in the eligible genotype group before it was available and then after when they were using it. Others of those studies have, instead of doing that sort of before and after comparison in the eligible genotype group, they've compared those people who are using ivacaftor because they have the eligible genotype with people seen in the same time period, but who were not eligible to get the treatment because they didn't have that genotype. And so we're going to refer to these as one of those as the time period comparison and the second as the genotype comparison. Later on, we'll also be looking at this sort of fourth group in the bottom right here, which wasn't involved in either of those comparisons, but we'll see later how this group of people in the, bottom left, so these ineligible people in the pre-ivacaftor era, how we might make use of that group as well. I'm also going to use this little grid on each slide to remind us of this setup of having these four groups in a 2x2 table of eligibility is defined by your genotype, and then we've got before and after. So G is denoting genotype and P is denoting the time period, and they're both binary. So hopefully this helps us to try and remember what's going on here. So the aim, just going back to what these other studies have done, was to think about, is that valid to use these control groups, either historical or contemporary, but in a different genotype group? Is it valid to use those groups as control groups? And if not, what can we do about it? So the first thing we wanted to do is really just to define clearly what exactly it is we're trying to estimate. So just introducing a bit of notation here. Y is our outcome, and let's think of a continuous outcome when we're thinking of this main outcome of lung function measured using FEV1 % predicted. And X is denoting our treatment variable, so that's 0 or 1. And then we're defining these counterfactual outcomes. So Y with the superscript X is 1 is the counterfactual outcome had a person received ivacaftor, and Y superscript X equals 0 is the counterfactual outcome had a person not received ivacaftor. And we only observe people obviously under one of those conditions. So here's the thing we're trying to estimate, our causal treatment effect, we'll call it the CTE. It's a difference in expectations of these counterfactual outcomes under treatment and non-treatment. And we've defined it in the treated, so we've conditioned on x equals 1. So it's really an average treatment effect in the treated. That's what's of interest to us, because there's no point in thinking about any of the, say, the ineligible genotype group receiving this treatment. That's not really a suitable question. Now, because everybody in this green group, in the little table at the top, is receiving ivacaftor, we can actually write this difference in expectations. We can replace the conditioning on x equals 1 with the conditioning on g equals 1 and p equals 1, so being in the right genotype group and in the right time period. So how can we estimate these two expectations? Well, this first one is easy to estimate. So everyone in that top right group, the green group, they are, in fact, everyone is receiving the treatment. And so we can estimate this expected counterfactual outcome just using the expected observed outcomes in that group of people. So that's very easy. It's this second term in the causal treatment effect that brings us a problem, because we don't have any people in that green group who are not receiving the treatment. Well, we're in the data, we have a very, very tiny number, but not a number which is big enough to help us estimate that thing. So this just goes back to what those other studies have done, really. We're going to call the treatment effects that they've used as the naive treatment effects. So, as mentioned, some studies, go back. Some studies made this before and after comparison, which is written using this naive treatment effect under the time period comparison here. So they've estimated that second term in the causal treatment effect using the people in the eligible genotype group, but before this treatment was available. Some of the other studies have used this other naive treatment effect where they've estimated that second term in the causal treatment effect using the people in the ineligible genotype group, but in the right time period. So what we want to look at is under what conditions do these naive treatment effects correspond to that causal treatment effect that we're really interested in, and how can we assess potential bias if those conditions are not met. And we use causal diagrams to try and explain and investigate this. So we're going to think of 3 different scenarios, sort of building up from something, from a simple DAG up to something which is more difficult for us in terms of this problem. So thinking of the DAG on the left there, we've got our outcome Y, X is our treatment, ivacaftor pointing to Y, so that's the treatment effect that we're interested in estimating. And in this simplest scenario, so G genotype and P time period, they're both pointing to X, they determine X. In fact, those are deterministic relationships. But in this simple DAG, they're not pointing to Y. So we're saying that sort of genotype and time period are not affecting the outcome apart from through their effect on X, which is probably not a reasonable assumption, because we know that things have been generally improving for the CF population over time. And also there are known to be differences in disease trajectories between people with different genotypes. So the second scenario has a link from G to Y and P to Y that doesn't go through the treatment. It goes through what we're calling these H variables. They represent health status, and these are measured health status variables. So in the application later, we put quite a large number of variables in there, like whether people have CF-related diabetes, what what other treatments they might be using, when they have certain infections, and so on and so on. But the key thing is that they're measured things, observed things. And then the third DAG, we have these direct arrows going from GMP to the outcome, so not through these observed variables H. So we're going to think of each of these things in turn, starting with this simplest case. And again, the aim here is about thinking about how we estimate this problematic or difficult second expectation in our causal treatment effect. So because this expectation in the causal treatment effect, it's defined in terms of this counterfactual outcome. So it turned out it was useful to think about our assumptions by making use of these single world intervention graphs, or SWIGs. And these were described in this 2013 paper by Richardson and Robbins. So this is a sort of causal diagram for a hypothetical world in which a particular treatment level is assigned. So here, because we're interested in the counterfactual outcome under no treatment, we've put x equals 0 here. So we've divided up the observed treatment from a hypothetical intervention. And then we've got our outcome, our counterfactual outcome over here. And what this helps us to do is to think about our assumptions. So what we see when we translate this DAG into this SWIG is we can see that this counterfactual outcome is independent of GMP, the way we've drawn this DAG. And what this means is that we can write this expectation, this second expectation in the causal treatment effect, which is conditional on G is 1 and P equals 1. Well, we've just said that that counterfactual outcome is independent of G and P, so we can just put any values for G and P on the right-hand side of that probability. So, for example, I could, instead of having G is 1 and P equals 1, I could write G is 1 and P equals 0. So that's for the top left group in our 2 by 2 table. And that group, no one was in fact receiving the treatment, and so we can write that expectation of the counterfactual outcome in that group is equivalent to the expectation of the observed outcome, which we can estimate directly from our data. Similarly, we could write G equals 0 and P equals 1, and again, that's our bottom right-hand group in our 2 by 2 table. None of those people received the treatment, and so we can again write this expectation of the counterfactual outcome as the expectation of the observed outcome. So this means we can write our causal treatment effect in these two ways under this DAG, as depicted here. These are exactly what we had written before as our naive treatment effects. We'll call those our time period naive treatment effect and our genotype naive treatment effect. So under the assumptions of that DAG, the prior studies which have used either one or other of these control groups are valid for estimating that causal treatment effect. So let's move on to this slightly more complicated situation where we do have these routes from G and P to the outcome Y, but they go through these measured variables H. And again, we can translate our DAG into this single world intervention graph and read off that some conditional independence assumptions or conditions that are valid according to this DAG. So according to this DAG, this counterfactual outcome Y is independent of G and P, conditional on these measured variables H. So what that means is that this expectation, well, we can't deal with this expectation directly, it requires just some extra steps. But after conditioning on H in this second expectation in the causal treatment effect, we can replace G and P by anything. After conditioning on H, that counterfactual outcome is independent of G and P. So this second expectation in the causal treatment effect, the first step is just to, we can average over H, so use standardization. And then looking at this first term in that sum, just imagining H to be binary or categorical for simplicity here. We've just said that we have this, according to our DAG, we have this conditional independence condition here. And so we can replace G and P by anything here. We could replace it by G is 1 and P equals 0. So that's again using the top left group in our 2x2 little table. And again, we can then use what we know about our data is that none of those people receive the treatment. And so this expectation in the G equals 1 and P equals 0 can be written in terms of the expectation of the observed outcome. And we can do the same using the other possible control group there. So under this, go back. Under this slightly more complicated DAG here, where we have these other routes from G and P to the outcome, if we've got these measured variables H, which those effects go through, then we can deal with that using standardization. So let's move on to this third final DAG here, which is the most difficult situation to deal with. So we've got these pathways from G and P to the outcome Y, which are not only through measured other variables. So again, let's translate that into this SWIG to help us think about these independence assumptions. Now this counterfactual outcome is not independent of G and P. And so this causes a problem for us. We can't use either of those approaches that were used in the earlier two DAGs, including by using standardization. So we need to do something else if we're in this type of scenario, which we possibly are. So this is where the idea of using negative control outcomes came in. So there's this nice paper from Lipsitch and others on negative controls, a tool for detecting confounding and bias in observational studies, which came out in 2010. So let me refer to some of the DAGs that they used in their paper. So slightly different notation here. We've got the outcome Y again, we've got the treatment A, and then we've got some measured confounders L, and then some unmeasured confounders here, U. So a negative control outcome is one that looks like this. So it has the same arrows going into it as the actual outcome, Y, except the one that comes from the treatment A. And so a negative control outcome is one that is such that the set of common causes of A and Y is the same as the set of common causes of A and this negative control outcome. So if we think about just in this scenario, trying to estimate the effect of A on Y, we would adjust for L, those are measured confounders, but we can't adjust for the U, those are unmeasured. So we think that that estimated effect of A on Y may be biased due to unmeasured confounding or uncontrolled confounding. Now suppose that we estimated the effect of A on this negative control outcome. Again, we do exactly the same analysis, so we'd again adjust for L. Again, we can't do anything about U because we don't observe it. But if there is no unmeasured confounding, then we should see a null association between A and this negative control outcome, because there can be no relationship there. Or there can be no effect there. But if we do find a non-null value for our estimate of the effect of A on this negative control outcome, that tells us there's something else going on. And under this DAG, we could attribute that to this unmeasured, sort of uncontrolled confounding by U. So that's the basic idea of negative control outcomes. And then in this other paper by Surfer and others, they again took this idea of negative control outcomes, particularly thinking about it in this context of unobserved confounding. And they described it as a generalization of a difference in differences approach. Excuse me. So this DAG here is really like this DAG we had on the previous slide, except I'm thinking of this negative control outcome as being a pre-exposure outcome. So here we've got our post-exposure or post-treatment outcome. Let's call it Y post, our treatment here. And this is a pre-exposure outcome. So the same thing, but measured before the exposure or treatment. And again, we've got these measured confounders L, unmeasured confounders U. So they show how we can use this pre-treatment outcome as a negative control outcome to investigate the possibility of unobserved confounding or bias due to unobserved confounding. And they then show how we can not only use this situation to detect bias due to unmeasured confounding, but also to make corrections for it using difference in differences analysis, which is what we've used here. So let me try to explain how we've applied this kind of approach in our setting. So here's our DAG again, with G and P pointing to Y. We've got our treatment X there. I think we can just reformulate this DAG to look like this one on the right here. So P is time period. We could instead sort of spread our DAG out and write Y as a pre-treatment component and a post-treatment component. So that the P here has just been dealt with by splitting the outcome into pre and post-treatment. All the other relationships are the same in this diagram. And then we have a DAG that looks quite a lot, well, not exactly, but quite a lot like the one that Surfer et al. Used in their paper. Now, a difference here is that G is not an unmeasured confounder here, but it's sort of an uncontrollable confounder because we don't have any variability in X within the G equal 1 and G equal 0 groups in this post-Ivor-Kafta era. So it's not an unmeasured confounder, but it is an uncontrollable confounder. So we've got this positivity problem. And so we've argued that we can use this same trick of negative controls, think about it in that same way to deal with this challenge here. So I'm going to think about this first of all in terms of, let's suppose that we using a comparison between these two groups here. So we're looking at the post-Ivor-Kafta era. We've got the observed outcome in all those people. We've got G. And then we're going to use the observed outcome in this pre-Ivor-Kafta era in these two groups. That's our negative control outcome here. So it's the outcome observed in those two groups before the treatment came into being. So let's see how we can use these four groups now to try and allow us, using difference in differences approach, to estimate this causal treatment effect in the scenario of this DAG. So there's our causal treatment effect definition at the top again. We can write this as a difference in differences. So all we're doing here is adding something on and then subtracting it off again and just rearranging our equation. So we've now written this causal treatment effect in terms of two differences. But this second term here in the circled in the blue is just the same thing, just a trick. So let's think about these two differences. This first difference, the first term is all good. That's the first term in CTE. We've already argued that we can estimate that from the data, no problem. This second term, we can also estimate from the data without any difficulty, because this second term, it's the ineligible genotype group in the post-Ivor-Kafta era. They were none of those people receiving the treatment. So again, this expectation of the counterfactual outcome can be written as an expectation of the observed outcomes. So that's how we deal with that first difference there. The second difference requires just a bit more thought, for me at least. So let's think about this linear model for this expectation. So here I've got the expectation of this counterfactual outcome, conditional on G and P, takes this linear form. And if we just write it out, we plug that into these expectations here, what we can show is that this difference in expectations can be written as we've shown at the bottom here. So all we've done is we've switched p equals 1 to p equals 0. A key assumption here is that in this linear model, there is no G by P interaction. So the sort of effect of genotype on the outcome does not vary in these two periods. I probably should have said before I did that, that we can't estimate, thinking about going back up to here, we cannot estimate this first term here for the same reason that we've discussed earlier. We don't have any people in this G equals 1, P equals 1 group where they were untreated. And so that's why we're going through this procedure, to use a trick and an assumption, which is no G by P interaction, that enables us to write this expectation, replacing P equals 1 by P equals 0. And then, again, we've written this in terms of a difference in expectations, but in two groups where nobody received the treatment. So again, we can replace this counterfactual outcome with the observed outcome, like I've done here. So using this difference in differences, we've written this causal treatment effect in terms of what we'll call the negative control corrected treatment effect. And we've written it in terms of not now using those arguments and those assumptions in terms of expectations of observed outcomes in these four groups that we have available in our data. So the first difference there is actually one of the naive treatment effects that we saw before. And then we're just subtracting off this other term, which is our, we'll call it our negative control effect. So let's just have a little look at this negative control effect. It's the difference in the outcome in that pre-Ivor-Caftor era, so before 2012, between the two genotype groups. Now, if in this period no one was receiving the treatment, and so if we see a difference between those two groups, we know that it's due to genotype, not due to treatment. If we see no difference there, we return back, well, this reverts then to this naive treatment effect. So if our negative control effect is 0, then that's really telling us that there's no direct arrow from G to Y that we need to worry about. So this is just basically a summary of that. So our naive treatment effect compares these people on the right in this diagram. The negative control treatment effect compares people on the left, where we expect no difference due to treatment. There can be no difference due to treatment in these two groups on the left. The only difference we can see there can be due to genotype. We can actually do this, go through the whole procedure again. You'll probably be pleased to know that I'm not going to go through all that again, but you can probably see how we can use the same trick to do it the other way around. So we can compare these people in the eligible genotype group before and after. We're concerned that some of that difference in those groups is not just due to treatment, but due to general improvements over time. And so we use this, we look at the sort of negative control outcome in these two groups at the bottom. There can be no difference in those two groups due to treatment because there is no one is treated there. And so any difference between these two groups in the bottom panel there must be due to things that have improved over time. So all of this again comes back to this assumption of no G by P interaction. So we assume that things improving over time in these ineligible people are also improving over the time in the same way in the eligible genotype group. So this is just a summary. We end up under this DAG with two possible negative control corrected treatment effects, both of which make use of these four groups, but just in a slightly different way. So going right back to where we started, I've considered these three scenarios that we might be in. In this DAG on the left, that causal treatment effect that we want to estimate can be estimated using those naive treatment effects, either using a genotype comparison or a time period comparison. If we have these measured variables H, through which G and P act on the outcome, then we can use standardization to deal with that. If we're in this third scenario, then we can make use of negative control outcomes to obtain an unbiased estimate of the causal treatment effect through this negative control corrected treatment effect. So lastly, in the last few minutes, I will just tell you about how we applied this to the CF data. So these are the numbers of people that we had in our four groups. So people in this eligible genotype group, there are, that's a relatively small group, as I said at the beginning, around about 400 people in that group in the pre and post ivacaftor periods, and much bigger group in the ineligible people. So we estimated all these various things using this data. We estimated naive treatment effects using the two different possible comparisons, the negative control effects and the negative control corrected effects. And yes, there are these two versions of each, using the time period comparison or the genotype comparison. So just briefly how we did the analysis for this continuous outcome of lung function measured using FEV1% predicted. So we have, let's suppose we're thinking about this post-ivacaftor era here. We've got longitudinal data from the registry, so we made use of that. So we used generalized estimating equations to model these longitudinal data, and we actually wanted to estimate what we call a step change effect and a slope change effect. So the step change is like an initial sort of boost in your lung function that you may get from the treatment, and then there's this slope change effect, which is the impact of this treatment on the slope of decline in lung function over time. So we set up a model, which I haven't given the details of here, to enable us to estimate both of those effects. So to estimate the naive treatment effect, we fit that model in these using data on these two groups here. In the green group, X is set to 1, and in the orange group, X is 0. To estimate the negative control effect, we use the other pair of groups, so in the pre-ivacaftor era. But what we do is that, go back. In this top left group here, we actually, even though X was 0 in that group, they were untreated, we set X to 1 in that group. And this is what, if the negative control effect is 0, then that will correspond to a 0 coefficient for the X in this model. Yeah, so we're fitting two models here, one to this pair, one to this pair, and then we do a subtraction to do the difference in differences to get our negative control corrected treatment effect. And we do the same sort of the other way around. We then fit a model to this pair and then to this pair. And again, here we use this trick of setting X equal to 1 in this right-hand group, even though they didn't receive the treatment, but what we're trying to assess is whether there is any sort of association between X and the outcome, which would be representative of a time period effect here. So let me just show you a flavour of the results. So here we've got results from the time period comparison and the genotype comparison. These are absolute differences. We've got the step change effect in lung function and the slope change effect. And then we've got our naive treatment effect, our negative control effect, and then our corrected effect. So one thing that we immediately, let's focus on this step change effect. So that's sort of the bump up in lung function that this treatment gives you. So a really obvious thing to notice here is that this negative control effect is really close to zero, either whether we do the time period comparison or the genotype comparison. So suggesting that there's not much change over time that has impacted on our treatment effect here. And there's not much difference in the genotype groups in terms of how genotype affects this change in lung function. Whereas the naive treatment effect is all the way over here, quite a big effect, about 6 percentage points in FEV1%, which is quite a big boost in lung function. And then the negative control corrected effect is, well, it doesn't change very much, but it's the difference between these two. And again, it's the same under the two comparisons, which is reassuring. And all of the confidence intervals here were obtained using bootstrapping. The slope change effect, we did the same thing. We found some suggestion that the slope of decline is less on the treatment, which is a good thing, of course, but the confidence intervals are overlapping zero quite a lot there. Just briefly, that we performed a similar analysis for another outcome, which was a count outcome, which is the number of days of using IV antibiotics over the course of 1 year. And the causal treatment effect for this outcome was, instead of being defined in terms of a mean difference, was defined in terms of a rate ratio. And so the analysis here used a negative binomial model instead of just a linear regression model. And so in a lot of places where we had differences for this approach, we have ratios of things instead of differences in things. And we looked at we looked at this rate ratio after 1 year of treatment, 2 years of treatment, and 3 years of treatment. And we see here that, interestingly, the negative control effect is practically zero in all of these cases. And so the naive treatment effect and the negative control corrected treatment effect is very similar. What this is showing, these are rate ratios, they're around 0.4, 0.5, so a substantial reduction in the rates of going into hospital with requirement for IV antibiotics, not just in the first year, but out to 3 years after starting treatment. So actually what these results suggest is that everything that all those other people did before in their earlier studies was probably perfectly valid, because there is doesn't seem to be much of this negative control effect, sort of contamination by time period or by using the ineligible genotype people as a control group. A couple of slides, just some discussion points and some other work we're doing on this. So we have shown that those naive treatment effects used in those early studies are valid only under quite strong assumptions, although it looks like those assumptions might be really not too bad here. Negative control outcomes can be used, however, to obtain unbiased estimates of that causal treatment effect under weaker assumptions. There are some other scenarios in which this also can be used, like when we've got I've just done a couple of scenarios at the bottom here, but when we've got these measured health status variables, but we have some unmeasured confounders of those health status variables and the outcome. So just a slightly more general setting in which these methods can be used, it can be shown. So something that I'm working on at the moment is that I'm currently working on extending this to estimating the effect of this treatment ivacaftor on survival, which is something that hasn't been looked at in any of the trials. They've been too short term. And then with the aim of then possibly using those results to estimate the potential impact of using this treatment over a patient's whole lifetime on their life expectancy. There's been a lot of developments in these treatments, as I mentioned near the beginning, over the past few years. Ivacaftor was just the first of these CFTR modulator treatments that was developed. There are others, and particularly recently, a treatment which is called, in the UK, it's called Kaftrio, it's called Trikafta elsewhere, was recently approved in the UK, and patients have now started to gain access to that treatment. And a particularly exciting thing about that treatment is that it works for a genotype group which is very, very common. So now they have these precision treatments that actually work on people on over 90% of the CF population. And so there's going to be a lot of interest, I think, in looking longer term, the real world impacts of this new treatment, which has just come into use. So I'll finish there. Let me acknowledge my collaborators again, and also our funders. So Simon Newsom's PhD was funded by a CF Trust Strategic Research Centre grant, and I am funded by UK Research and Innovation. Thank you very much for listening, and I'll be very happy to hear people's comments or questions.
Thank you very much.
Right, whether is this a negative control outcome or is it a negative control exposure? And yeah, we eventually sort of decided that it was a negative control outcome, but because it doesn't quite, it doesn't quite fit into the previous descriptions of negative control outcomes, I can see that is some debate there. So if the person asking the question had some detailed thoughts on that, I would be really interested to hear about that, whether they think it could also be thought of as a negative control exposure, particularly the second situation where we're not looking before and after, we're looking between genotype groups.